This presentation is going to cover the finite dipole, and it is the logical conclusion to the previous presentations, which have started from an accelerated charge which we can think of as a non-relativistic electron, which gives us the power radiated, which is equal to the charge squared times the acceleration squared divided by 6 pi times c cubed times epsilon naught, and that is nothing more than the Larmor formula. Then we went on to the infinitesimal dipole, and we note in passing that the length of our antenna must be 1/50th of the wavelength of interest for this infinitesimal dipole analysis to apply. The radiation power for the infinitesimal dipole was seen to be Z naught, which is the characteristic impedance of vacuum, times the wave number, times the maximum current, times the length of our antenna, quantity squared, divided by 12 pi. Then we went on to study the small dipole, which has an analysis that is applicable to lengths of antenna smaller than 1/10 of our wavelength of interest. And we came up with the radiation power expression to be Z naught times K I naught L quantity squared divided by 48 pi. So these three expressions all led us to this point where we are right now to study the finite dipole. The math we're going to see is going to be a little bit more interesting, but the analysis is going to be similar to what we've done before. We're going to start from currents, then we're going to go ahead and get electric fields, magnetic fields, Poynting vectors, and then finally our radiation expressions. So let's start. We start with the finite dipole, and for that we start with a current distribution that is much more realistic than any we've seen in the past. Current distribution as a function of r, coordinate r, is essentially going to be a current distribution in terms of the prime coordinates, and we're going to take x and y to be the origin, and it's going to be an antenna that is along the z-axis, the positive z-axis and the negative z-axis. It's going to be sinusoidal, and either the positive or the negative areas. So we're going to express it by saying it's going to be the sine of this term, notice the minus sign, from 0 between z prime between 0 and L over 2. And it's also going to be this term right here, notice the positive sign for z between minus L over 2 to 0. And once we use this expression, we'll actually come up with the analysis for the finite dipole. And of course we see that we go back to the expression that we derived with the infinitesimal dipole, and we consider the infinitesimal displacement z prime along the z prime axis. And we're going to look at the geometry here in a minute, and that's going to be contributing an infinitesimal component for the electric field in the theta direction. That's going to be almost equal to I z naught k, I over r, our current distribution over 4 pi, times e to the minus I k big R over big R times sine theta dz prime. So once we have that, let's go ahead and look at what our geometry is going to look like. Geometry is going to be a rectangular Cartesian coordinate system. We're going to have a point P, and we're going to have a vector R, big R, and a vector little r going from the origin. And the big R is going to be coming from the length element dz prime, which is going to be z prime above the origin. And again, the dipole is going to be L over 2 in the positive direction and L over 2 in the negative direction. So in the far field approximation that we're going to look at, big R is going to be almost equal to little r, and theta is almost equal to theta prime, but not quite. This is actually how we're going to proceed with this approximation. We're going to say that big R equals to x minus x prime quantity squared plus y minus y prime quantity squared plus z minus z prime quantity squared. We're going to simplify this by taking x prime equals to y prime equals to 0, and that gives us this expression. When we multiply out the z minus z prime expression, we get the z squared out, and then we can see that that is a term, another way of writing r squared. Then we can also simplify by seeing that z, this direction, is going to be r cosine theta. So this component is going to be r times the cosine of theta. So once we have that substitution here, we're able to see that big R equals to little r squared, square root of, plus this term right here. So that is what we're going to be looking at. But before we do, let's look at that expression a little bit closer. Specifically, let's factor out an r squared, a little r squared. Since it's underneath the square root, it comes out as r. And then we use something called the binomial approximation, which applies when this secondary term is relatively small speaking, which is what we're seeing. In those cases, the binomial approximation tells us that we can take the exponent and multiply it times the second term, which is exactly what we've done here. There are going to be higher order terms that we're going to look at here in a minute. So then what we have is that big R is approximately equal to r times 1 minus z prime over r, 2's cancel, and then the 1/2 comes up here in front of this term. And then the first one of the higher order terms is considered here, which is the square of this term. So that's why we get z prime squared cosine squared theta. That's where that comes from. Once we do that, we see that we can simplify this a little bit more by noting the following. We end up with, after we multiply times the r outside of the parentheses, r minus z prime cosine theta plus this term comes out in both of these terms, 1/2 z prime squared over r, and that's a 1 minus cosine squared of theta. And that, of course, is the definition of sine squared of theta. So our final expression for r in the far field approximation is r more or less equal to r minus z prime dot cosine theta plus this term right here, z prime squared sine squared theta, which we're going to neglect. But that would be the next term that would be of importance. So then let's write down in a summary what our far field approximation is. The far field approximation that we're considering is that the phase terms are going to go as r minus z prime cosine theta. Big R goes as little r minus z prime cosine theta, and the amplitude terms are going to go as r. So when we apply that approximation to our infinitesimal component of the electric field, we come up with dE theta almost equal to, or nearly equal to, these constants times e to the minus I k little r over little r. And since that r is in the phase, it's got a phase term approximation, it includes this term right here. That's where that comes from. Since it's an exponential, the addition of exponential terms results in a multiplication of exponentials, which is what we have right here. So once we have this now, we can group similar terms together. Specifically, we start grouping the prime terms. Since this is an analysis with respect to z prime, we can go ahead and group the prime terms to the very back here, and all the non-prime terms go to the front. The idea being that those terms then can fall outside of this integral from minus L over 2 to L over 2 of the infinitesimal electric field elements. And that would give us our total electric field. So then we can write down again that the electric field total would equal to these terms times the r dependence times the sine theta dependence, which we group in the front and pull out of the integral and call that the element factor, and everything with the prime coordinates underneath the integral with respect to dz prime, and call that the space factor. So that then becomes our electric field for the finite dipole. Immediately we can come up with a similar expression for the magnetic field. Notice that this one is in the phi direction, almost equal to, or nearly equal to, an element factor times a space factor. The only difference between the electric field and the magnetic field being this characteristic impedance of the vacuum. So then our problem becomes, once we insert our current, which is a realistic current of sines, with a plus z prime here and minus z prime here, it becomes this long expression. We notice that either one of these integrals can be solved by referring to mathematical tables or the Wolfram Alpha, or any online integration tool that shows that this integral, notice there's a plus c, there's a phase term here, results in this expression. So the problem from now is going to be to fit our terms into this expression and see where we go. To be very methodical, we're going to go ahead and split the total integral into two parts. The first part is going to be minus L over 2 to 0, and the second part is going to be 0 to positive L over 2. That way we keep our terms separate. Okay, so the first integral is going to be e to the ax over b squared plus a squared. It's the same term as before, but now evaluated from minus L over 2 to 0. As soon as we start inputting the 0 integral upper point of integration, we notice that we end up with e to the 0, which goes to 1, e to the 0 going to 1. This term right here, that subterm goes to 0, so that gives us a cosine of c and a sine of c, plus the lower integration boundary, which gives us this term right here. So now we're able to go ahead and simplify that a little bit more and write down so far a result for I1, the first integral, to be a sine c minus b cosine c plus these other terms. Now we go look at the second interval, the second integral, which is the same integral over a different interval. So it goes from 0 to L over 2. We do the same analysis as before, and just like before, the 0 limit of integration gives us e to the 0, and some cosines. We can simplify that a little bit, and we get this equation right here. Notice that that has become minus a sine c plus b prime cosine c. It should be noted that we're going with b prime as opposed to b, because that's where that negative sign of the sine function goes into. Remember, the current term had two expressions, the sine plus z and a sine minus z. So that's why we're differentiating with b prime in order to keep our algebra straight. Once we do that, we're going to go ahead and then add I1 plus I2, our two subintegrals, to come up with our total integral. And we come up with this expression here. It's very long, but we're able to start canceling out terms. Notice that this is where that b prime strategy comes to help us out, because if we had put down b, we might have been tempted to go ahead and cancel minus b cosine c with plus b prime cosine c, but we cannot, because there's a sign implicit in that b prime term. So once we have that, we can go ahead and now start substituting back our terms to solve our equation, our integral equation initially. So first we say c equals to kl over 2. When we say that, we start putting in here kl over 2 instead of this c, kl over 2 instead of this c, and here, similarly, we start replacing kl over 2. And then on the final term, minus b cosine c becomes cosine kl over 2, plus b prime cosine c becomes plus b prime cosine kl over 2. So again, all we've done here is just started replacing c into our expression for the integral. Next, what we do is we replace these two terms, b equals to k and b prime equals to minus k. That's that important negative sign that we were just discussing. That gives us the following. That gives us, when we put in b here, minus kl over 2 plus kl over 2, that goes to 0, and that's a cosine of 0, which is 1. This term goes to 0, the sine of 0 goes to 0, and similarly over here. So we start noticing that a few of these terms are dropping away. Okay. Next, we go ahead and replace the final term, a equals to I cosine of theta times k. So when we do that, we start noticing that our integral becomes 1 over k squared plus a squared now becomes 1 over k squared plus this term, quantity squared. And then the next thing we do is we replace ik cosine theta here and here. When we do that, we notice that we end up with e to the minus ikl over 2 times cosine theta and e to the ikl over 2 cosine theta. That expression then looks very much like the definition of the cosine if we divide by 2, which is exactly what we do. We divide by 2 and multiply by 2, and then factor out the 2. There was a k that also got factored out from here, and we ended up with 2k divided by, also we factored out k squared here, and ended up with 1 minus cosine squared theta in the denominator, which of course is sine squared theta. One of the k's cancels in the denominator, and the k cancels in the numerator. And our final expression then for our integral is I equals to 2 over k sine squared theta times this cosine of a cosine term minus cosine kl over 2. Once we have the integral, now we can go back into our expression for the electric field, which remember was electric field in the theta direction approximately equal to these constants times e to the minus kr over r times sine theta times our total integral, which was I1 plus I2. We have I1 plus I2 from the previous page, so we can just replace that in here. We notice that immediately k cancels in the denominator and numerator. Sine squared, one of the signs cancels in the denominator, and it cancels altogether in the numerator. 2 cancels here and gives us a 2 left behind. Once we have that, we write down the expression for the finite dipole of the electric field. It's these constants times e to the ikr over r times this term cosine kl over 2 cosine theta minus cosine kl over 2 quantity divided by sine theta. Now, many times you'll see this written down in a variety of places, this equation, cosine of a cosine and such. And this is how we get to it. This is actually how you arrive at this expression. So now we know. After we know the electric field, we immediately divide by z naught, and we get the same expression divided by z naught, and that's the equation for the magnetic field. Again, there's the cosine of cosine. I put 1 over sine theta on the front, and other than that is the same. Following that, we find out what the pointing vector averaged would be. It would be 1/2 times the real part of this product. And notice that the magnetic field comes in as a complex conjugate of the magnetic field. That means that for every I, gets replaced with a minus I. So that becomes a plus I in the exponent. That I right there goes to minus I, which then multiplies times the I in the electric field. Negatives cancel, and that gives us a positive expression. Specifically, it gives us the unit vector in the r direction times the characteristic impedance times a lot of these terms squared, which you can see here. Specifically, there's the cosine of the cosine term over sine theta. That's a quantity squared for the average pointing vector. Once we have the average pointing vector, as we've done in previous derivations and presentations, we integrate over the complete sphere, and we come up with the radiation power expression. And in this case, that expression is multiplied, our cosine over cosine expression is here. It gets multiplied times the surface element for the integration, which is r squared sine theta. So one of the sine thetas cancels in the denominator, and r squared cancels here. And we have an integral from 0 to 2 pi, only with the d phi dependence here. So that one we can readily integrate, and that becomes phi evaluated between 0 and 2 pi. The 0 component does not contribute, the 2 pi component does, and it gives us a 2 pi here. We of course see then that as we write this down, the 2 pi will cancel 1 pi down in the denominator, and 8 becomes 4, and that's our expression. And that is a definite integral that we write down in our expression. Notice here that you have an expression that has k and l. So if somebody gives you the wave number and the length of your dipole antenna, you can go ahead and evaluate this using Wolfram Alpha, an integral evaluation tool online, or mathematical tables, what have you, and come up with a number. So this entire expression is actually just a number, okay? And so again, remember k is the wave number, so that's 2 pi over lambda, times some constants in the front. Now, in passing, we should note or remind you that Z naught is the characteristic impedance of the vacuum. So that is equal to the square root of mu naught over epsilon naught, or 377 ohms. So once we have the radiation power, we also note that we can have that expression for power equals to 1/2 times this quantity called the radiation resistance times I naught squared. So we set that expression equal to the expression that we derived in the previous page. There's our integral right there, and we get this. So multiplying by 2, the 2 comes over here, divides out here, simplifies to 2, I naught squared cancels, and we're left with this expression for the radiation resistance of an antenna, of a dipole antenna. Now, remember that the radiation resistance is one of two components that come into the radiation, to the resistance for an antenna. One is the radiation resistance, which is the effect of the atmosphere that we're radiating into. And also the second term would be the ohmic losses or any sort of losses of the current in our antenna. But this expression is quite important. It's the radiation resistance. And it's interesting that we come up with something that looks a little bit daunting, but remind you that we know a lot of this stuff. Z naught is 377 ohms, 2 pi is a constant, and this entire number evaluates out using a variety of techniques like Wolfram alpha once we're giving a wavelength and a length of our antenna. So what we have is k is 2 pi over lambda, L is the length of our antenna, and that becomes a number. So after this presentation, then we see that the expression for radiation resistance is something very self-contained. And again, this is for a finite dipole. So finite dipole being something from applicable for a length of an antenna that is between 1/10 of the wavelength of interest to maybe even 3 times the wavelength of interest. So that concludes the presentation, and that concludes the series so far, arriving at the finite dipole derivation.